So the first speaker is la profesora Raquel González Arrabal from the Institute of Nuclear Fusion, Guillermo Velarde of UPM. Raquel is already a professor at the university. Is a real very specialist in nanomaterials, in materials under very extreme conditions.
Yeah.
So she applied many techniques that she will talk to you today to analyze and characterize materials under irradiation or under pressure, no? By different techniques. She is the leader of the laboratory that we have in the institute, where there are facilities for sputtering, for permeation, for treating, well, not treating, but gas permeation, and manufacturing of nanomaterials. So, characterization techniques of materials under irradiation. Please, Raquel.
Okay, so thank you, Manolo. Thank you for this very nice introduction, and thank you also to the organizers for giving me the opportunity to talk about these very fascinating things, okay, which is materials under irradiation. Well, the content of the talk is as follows. So first of all, I'm going to see what material characterization means, and we are going to review very briefly, okay, because it has been done previously, the irradiation conditions in nuclear fission reactor. And basically, we are going to do it because depending on the irradiation conditions, we are going to have differences in the radiation-induced damage. Then I'm going to, again, briefly review the radiation-induced damage into the material, and then I'm going to show you how to choose the proper material characterization technique, which is really a very difficult task. And then finally, we are going to see some real examples. So the motivation, as you already have seen, it is that, well, material is really a key point for fusion, okay? With materials, we are not going to have any fusion reactors. Basically, to have the reactor working is materials able to withstand the very harsh conditions, not only the very large radiation environment, but also the very large thermal loads taking place in this kind of reactors, okay? So the main challenge trying to develop more radiation resistant materials, it is to characterize the materials, well, before, you know, during irradiation. And well, here I showed you a brief layout, okay, about this is a cross-section of the two reactors, okay. This is going to be in the inertial confinement fusion approach, and the other one is going to be in the magnetic fusion approach. But you may see that in both approaches, basically, we have the so-called plasma-facing material, or first wall, in the inertial confinement reactor, which is going to be the material directly exposed to the explosion threads or directly in contact with the plasma, in the case of a magnetic fusion reactor. Then we are going to have the structural material, which is going to be basically a steel, okay, located here underneath the plasma-facing material. And then, as David already explained yesterday, we are going to have the breather blanket, okay, which is going to be able to produce the tritium needed for the reaction to take place, okay? So this is basically the layout in the both configurations. So material characterization means, well, basically, material characterization involves to answer 4 questions, okay? This is what is the elemental composition of the material, because the material properties are going to depend on the elemental composition, in particular in impurity and defects, okay? What is the crystal local structure of the material, and what are the defects, and, well, how is the material performance, which is very much related with the other 3 questions. So, well, okay, these are the questions we have when we try to characterize material. And then what are the proofs we have? Well, basically, we have a lot of proofs, okay? So we have ions for diagnosis, we have electrons for diagnosis, we have photons, neutrons, and positrons, okay? So, well, if we try to summarize the all available characterization techniques, we end up with thousand of available techniques, okay? So I'm not going to go very deep into the particular details of every technique, okay, because it will be the subject of a summer school, okay? But I'm going to try to summarize more or less what for every particular technique is used. So for example, if we are focusing on a structural or microstructural characterization, then we have to define if we are interested on the sample surface or if on the contrary we are interested in the bulk, okay? If we are interested in characterizing the bulk structure, for example, well here I plot the techniques. You may see that the red techniques are related with ions as proof, the green techniques are related as electrons as proofs, and so on. Photons is blue, and so on, okay? So if we are interested in characterizing, for example, the bulk structure, then we have X-ray diffraction or transmission electron microscopy in both pure transmission or high-resolution transmission electron microscopy or neutron scattering, okay? On the contrary, if we are interested in the surface structure, then we have scanning tunnel microscopy, ion channeling, low-energy electron diffraction, okay? If we are interested on topography, on surface topography, then we have the very well-known optical microscopy or scanning electron microscopy, atomic form microscopy, ellipsometry, Fourier transform, infrared spectroscopy, elastic neutron scattering, and so on. And if we are interested in microstructure, so meaning impurities, vacancies, interstitial grain boundary dislocations, grains, and so on, cracks, and so on, then we have a small angle X-ray scattering, Raman and positron annihilation spectroscopy, among others, okay? If we are interested in chemical characterization, again, we have to distinguish between bulk and surface. If we are interested in the bulk composition, we have spectrophotometry and mass spectroscopy, and if we are interested in surface composition, we have the whole family of ion beam analysis techniques, and we have J-electron spectroscopy, secondary ion mass spectroscopy, and so on, okay? So, well, all these techniques, this is only a small sample of the techniques we have available. So to choose the proper techniques is really very challenging. And it is the key point, okay, if we want really to have a proper characterization of materials. So then, well, as you may realize after this introduction, material characterization is really a very complex process, okay, which usually, and this is a very important point, okay, which usually requires the combination of more than one technique, okay? So in order to properly characterize the material, we need first to identify the properties to be analyzed, okay? We need to know if we are interested, for example, in knowing the permeation of barriers or whatever. And we have to choose the right characterization techniques for a given question, okay? So, well, let's first to identify the property to be analyzed. And in order to do that, let me introduce, okay, what kind of defects radiation produces into the material for you to realize what is the kind of defect or what is the kind of answer we are looking for, okay? So basically, as you have already listened during the course, okay, the radiation-induced damage into the material depends on both the radiation environment, but also, and this is not a minor task, okay, it is very important, it also depends on the native defect configuration, okay? It depends on the as defect configuration in the sample. So then the first thing that is necessary to know, it is the radiation environment that the material will face, okay? So we need to know if we are dealing with X-ray or if, on the contrary, we are dealing with neutrons, ions, and so on. We need to know the fluence, okay? We need to know the flow. We need to know the radiation temperature, the energy of the species, and this is also very important, okay? We need to know the radiation nature. So we need to know if the material is going to be irradiated under pulse irradiation or under continuous irradiation, okay? Because the radiation effects are going to be different in both cases. And in the case of using pulse irradiation, okay, as the case of the inertial fusion confinement reactor, then we also need to know the pulse duration, the repetition rates, and this is very important. We also need to know if the sample experiments thermal loads concurrent to the radiation damage, okay? So these are the things we need to consider. So basically, as you have already seen, the radiation environments on the reactors basically depends on the confinement approach, okay? If we are dealing with magnetic fusion or if we are dealing with inertial fusion. And in the particular case of inertial fusion, as Dimitri was pointing out this morning, it depends if we are dealing on the direct drive configuration or in indirect drive configuration, okay? Well, as Mike was pointing yesterday, we may have a wet wall or a dry wall, then the conditions are going to be different, and also the locations of the material in the reactor, okay? So basically, this is a table, okay, to summarize the most important threats that the material have to withstand when located in the reactor. So here we identify ions, okay? Ion is going to be the main threat basically for plasma-facing material, okay, because the penetration rate for neutrons is very long, so the first wall of the material basically is not going to see the neutrons, but ions. And then we have to make a difference. If we are dealing with magnetic fusion, we are going to have low energy ions. Sometimes the energy of this low energy ion, it is below the so-called displacement damage threshold, okay? But they are going to still to produce damage because of other factors, okay? And in general, the irradiation is going to be continuous, with the exception of the divertor, okay? In the divertor, we are going to receive pulses because of the plasma inhomogeneities. If we stay on ions, but we go to the inertial fusion reactor, basically we see that, well, we may distinguish between the ions produced directly by the bound products, and in this particular case, we are going to have very high energetic ions, okay? The average energy is going to be around 2 MeV. And, well, the pulse, they are going to be pulse with a pulse duration of hundreds of nanoseconds. And if we have debris, then the energy is lower, but still it's much higher, order of magnitude higher than the one we have in the magnetic configuration. It's going to be 150 kV on average, okay? And this is going to be the pulse duration. If we have the indirect drive, then ions, it's not going to be such a problem, okay? Because what we do is we are going to inject a gas in the chamber directly to stop those ions reaching the plasma phase material. Well, these ions are going to be particular threats for plasma phase material and final lenses, okay? So they are going to affect those materials. Then we are going to have X-ray when dealing with inertial fusion, okay? Dimitri Batani was explaining this morning. And, well, this X-ray, they are going to have an energy of around 10 kV, okay, average. In the direct drive configuration, and the pulse duration, it's going to be in the range of few nanoseconds. And they are going to be especially deleterious in the case of the indirect drive configuration, okay, because a large amount of X-ray are produced out of the whole RAM, okay? And, well, this X-ray are going to affect mainly the plasma phase material, and what they are going to do basically is they are going to hit the material. Well, the energy deposited by those X-ray in the material is so high that they can even melt the material, just without considering nothing more than the energy deposited by radiation in the plasma phase material, okay? And then we have neutrons, 40 MeV, and almost continuous in magnetic fusion, 12 MeV, and well, basically pulse neutron, okay? This was the question that Manolo was asking yesterday to Angel Ibarra. What about it, me? Can we have pulse neutrons, okay? And then they are going to affect basically the final lenses, the structural material, and the breather blanket, okay? So this is an overview about the damage we have to characterize, okay? This is only to show you, okay, this will be the plasma phase material, and you may see the X-ray deposit the energy here, deuterium, tritium here, helium here, and so on. And neutrons, they penetrate up to the structural material and underneath it, okay? This will be the layout. Well, Then we need to identify what kind of gametes are going to produce this radiation. So basically, neutrons are going to produce atomic displacements, okay? When the neutron energy it is above a certain energy threshold, what it is happening it is that the neutron is impinging into the sample, and then one lattice atom is displaced, is kicked out of this lattice position, and it is becoming an interstitial, okay? So this here creates a pair which is vacancy and interstitial. This pair is called Frenkel pair, okay? So we are going to have vacancies and interstitial Frenkel pairs. Well, it is not that easy as this picture, okay? Because if the energy of this knockout atom is large enough, what it's going to do, it is going to further displace more atoms, okay, creating what is called a collision cascade. Moreover, those defects can evolve, okay, and they can create bigger vacancies, which are going to be called voids, and, well, a larger number of interstitial. But neutrons, as told by Rafa Juarez, okay, this morning, also create transmutation reactions, okay? And transmutation reactions mean that neutrons create foreign elements into the sample. So they create helium, hydrogen, and its isotopes, okay? For example, in the case of tungsten, well, they may decay to rhenium, osmium, and so on. So the chemical composition, the elemental composition of the sample is going to change. Well, they also create gamma rays, but this is out of the scope of the talk. In the case of ions, we have to remember that ions have two different energy regimes, okay? If we have low energy ions, they basically, the nuclear stopping power is going to be much larger than the electronic stopping power. So those ions are going to produce atomic displacements, okay, as in the case of neutrons, okay? And when we have electronic excitation, so what the electronic stopping power is much larger than the nuclear stopping power, then the mechanism is it's different, it's completely different from this one. So the ion energy, it is transmitted to the electron lattice, and then from the electron lattice, by different mechanisms, it is translated to the atoms, okay? And finally, we can create ion tracks, okay? Those ion tracks can't even be regions of molten tracks within the material, because the deposited energy, it is, again, huge, okay? So this is basically a very schematic picture of the thing we are going to have, okay, after receiving the different things of radiation. So we may have interstitials, okay, which can be of the same material or a different material, okay, transmutation species, for example. Then we may have also vacancies, which, as you may realize here, produce a lattice distortion. But vacancies and interstitials are mobile, so we can have clusters of vacancies. So we may have voids, okay, so really voids. And at the same time, we have voids and we have gases. So we have helium, we have hydrogen, and its isotopes. So what's going to happen, it is that the gases are going to come to these voids here, and they are going to form bubbles. Okay, and when the helium or hydrogen content is large enough, what is going to happen is that these bubbles are going to be overpressurized, and then finally the material is going to crack. Okay, so then this is what I was explaining to you. Okay, here you may see some bubbles. This is the scanning electron microscopy picture of the tungsten sample after being irradiated with helium in a pulse way. And you may see here some bubbles. Okay, and here you may see that the sample crack directly. Okay, so we need to characterize both. We need to go from here to here and the other way around, okay? And this is why we need different characterization techniques. So, well, what are these very specific defects producing in the macroscopic properties of the sample? So what are the macroscopic chains we can observe? Well, basically, transmutation produces chains in the elemental composition. Then the chemical composition, it is also modified by diffusion, so the formation of new chemical phases and segregation. The volume, the example, also chains by Schwalling, okay, volume shape or shape chains, crepe or fuzz, and the physical properties, okay. Typically, the electrical conductivity decrease and the thermal conductivity also decrease. And while they also produce, as Angel Ibarra was telling yesterday, change in the mechanical property, hardening and loss of ductility, and so on, and in the optical properties, okay. So this is what we need to characterize. These are the techniques we have, and then the question it is how to choose the right characterization techniques. Well, unfortunately, I have not a universal answer, okay, but all I can do it is I can give you some hints of how to proceed. So first of all, we need to identify the information we want to obtain, so the property which is really interested for us. Then we need to establish the resolution limit we want. Do we want to see individual atoms, or on the contrary, we want to see clusters, or we want to see cracks? What is what we want to observe? And then this is a very important thing. We need to start with the easiest, cheapest, and more accessible technique to take basically the basic information that we need, and from that point on, we can move to more sophisticated techniques, okay? So, well, what are additional considerations? So basically, we need to know if we can make use of ex situ techniques or in situ techniques, okay? If we want to characterize the material response during irradiation, and if we can use destructive or non-destructive techniques, okay? These are also other limitations we have. Well, this is only a picture to show you how we were matching the different techniques depending on the answer we expect. Okay, so here you may see the defect sites we have. Okay, and here you may see the depth in the sample, okay? This will be the sample surface, and this will be the distance underneath the sample surface. So if we want to identify very small defects, okay, with in between 1 and 2 and 10 angstroms, and we make use of positron spectroscopy, basically, to identify those defects. Or on the contrary, if we want to identify very large defects, okay, well, large defects mean in the micrometer range or even below the micrometer range, then we go to optical microscopy. So meaning that if we have to choose a techniques to observe these defects, we are not going to use positron spectroscopy, okay, because optical microscopy is going to give us the answer we are looking for, okay? Well, then, if we have here in between the resolve site of optical microscopy and positron spectroscopy, we have a scanning channel microscopy or atomic force microscopy if defects are located on the surface, or we may go, for example, to transmission electron microscopy or X-ray scattering if defects are located underneath the sample surface, okay? This is dependent on the defect size, but we have also to consider what is the defect concentration we are expected. So, and then here again, I show you a very much similar picture in which I plot the defect concentration as a function of depth. And you may see this here, it is 1 ppm, 10 ppm, so on, 100% of the total concentration. And this is as a function of the sample depth, again, underneath the sample surface. And well, you may see here, again, that if we want to study very small defects, okay, then, or a very small defect concentration, then the only possibility is to go to positron spectroscopy. And if we want to study a larger concentration of defects, then we can go to atomic force microscopy, or if they are very large, we can go to optical microscopy. Okay, so depending on the size and on the defect concentration, we can choose one or the other techniques. Okay, so well, basically, this is all what I wanted. This is the introduction I wanted to do. Okay, for you to know what we are interested in studying, and then I'm going to show you a couple of examples, okay, of studies carried out in different materials, located at different locations in the reactor, and you may see how we can get a general picture of the material performance by combining the different techniques. So in this particular case, our objective was to study the behavior of tungsten under low energy irradiation, okay? So magnetic fusion conditions. Here the tungsten surface was irradiated with 60 electron volts at this fluence, okay? And the sample temperature was 773 kelvins, okay? So basically, this is a scanning electron microscopy picture. This was the sample before irradiation, and this was the sample after irradiation, okay, after plasma irradiation. You may see that the sample morphology has been modified just when exposed to helium irradiation. In particular, you may see it's much better when we take the cross-section of the sample, okay? You may see here that the kind of fuzz, so a kind of nanophone has been formed on the tungsten surface when exposed to the helium plasma. And if we measure the thermal conductivity of this material, we observe that it decreased by a factor of 10. Okay, so that this morphology change, the thermal conductivity in this layer produce a decrease of 1 order of magnitude in the thermal conductivity of the material. So this is indeed very bad news, okay, because we want the plasma facing material to have a very large thermal conductivity. Okay, then well, this is another example, okay? In this particular case, the tungsten was studied, but not under magnetic fusion conditions, but under inertial fusion conditions, not pulse, but high energy ions, okay? 350 keV, and we observe a very much different behavior. Okay, so remember the radiation conditions, the radiation damage depends on the radiation conditions. So here we use the same ion, okay, we use helium, but a much lower energy. And then what we observe it is some blisters on the sample surface, okay? So helium has formed bubble on the sample surface. And well, then if we analyze by using the positron annihilation spectroscopy, the behavior of the sample, basically this here, the black line corresponds to the unirradiated state, okay? And here basically we see a peak at 10 keV, okay, which will basically tell us that as the positive sample, so the sample contains before irradiation already contains some defects, okay? So those defects are basically related with dislocations and on impurity clusters which are related with the manufacturing process or with the polishing process of the sample, okay? And then, well, we observe a small enhancement of the signal after irradiation, okay? And then a further enhancement after irradiation and annealing. Okay, well, this basically this enhancement here shows us that well we have introduced some defects into the material, so we have introduced vacancies into the material, and well, this enhancement is lower than expected. Okay, and this is basically well because helium is introduced into the vacancies, and then the positron the positron emission is different. Okay, and if we have only vacancies without helium inside. And then, well, we observed that when we irradiate the sample, when we anneal the sample after irradiation, then, well, basically, again, the radiation response increased, okay? And it is not only that it increased, it is also that peaks are a little bit shift, okay, to much higher positron energy, which basically means that what we are going to have, it is helium vacancy clusters distributed all along the penetration range of the helium atoms, okay? Well, this could be, what is the time? No. 5 minutes more. Okay, so this is another thing I wanted to tell you. Well, we have a very much similar behavior when we were irradiating the samples not with helium but with hydrogen at high energy. Okay, again we see that we have some blisters. And in this particular case, this is particularly interesting because we were studying the behavior of nanomaterials under irradiation, okay? So we know that the coarse-grained tungsten is not going to work under inertial fusion conditions, okay? And we were trying to test the capabilities of nanostructure in tungsten, okay? What is going to happen if we introduce a large density of grain boundaries into the material? And then basically in this particular study, we were studying coarse-grained tungsten, so commercial tungsten, and we were studying nanostructured tungsten, okay, which was deposited by us. It was deposited by a sputtering as the one you may see here, okay? So basically, we aim to study the hydrogen death profiling as a function of the morphology and as a function of the irradiation conditions, okay? And then we were characterizing the hydrogen death profile, so how was the hydrogen distribution into the material by making use of resonant nuclear reaction analysis, of nuclear techniques, okay? So we use ions to characterize the effect of ion irradiation into the material, okay? So, well, this was basically, we carry out scanning electron microscopy studies. This is the cross-section and the top view of a nanostructure sample. And this is before and after irradiation. Okay, and well, we were taking special care with dealing with nanostructure materials because nanostructure materials are metastable materials. So the first thing we need to know it is that the material is not modifying because of irradiation, okay? That we have exactly the same material, the same morphology of the material prior to and after irradiation, okay? And well, here we have exactly the same material. There is no difference in between the material before and after irradiation. We were carrying out XRD studies, okay, to see the formation of secondary phases because we were irradiating the samples first with carbon in order to create vacancies, and then with hydrogen in order to see the behavior of the material in the pre-damage, okay, in a material which already contains a certain amount of vacancies, and we see no change in the chemical phases of the material, okay? And then, well, we were carrying out experiments in which we have characterized the hydrogen content into the sample as a function of them. And we were doing it by using nitrogen 15 out of this nuclear reaction. Okay, so here, the black line, it is the hydrogen distribution as a function of depth for a sample, nanostructure sample irradiated with hydrogen, and the red curve, it is the hydrogen distribution as a function of depth for a nanostructure sample which has been previously irradiated with carbon in order to create damage, and then with hydrogen in order to see the hydrogen behavior. And well, what we observe it is that in principle in nanostructure material, okay, there is no difference between the sample without vacancies or with vacancies, okay, the hydrogen, both curves are almost the same, okay? But in the coarse-grained sample, so in the commercial sample, we see that there is a very much different, a very large difference when we introduce vacancies before irradiating with hydrogen, okay? You may see that the hydrogen content is strongly increased, okay? So, well, this result is very hard to be interpreted by itself, okay? So what we have to do is we have to go to computer simulations, and this is, I have to say that this is really a very important point, okay? So as far as we can, we have to perform computer simulations and experiments, both computer simulations to really understand the results of the experiments, and also experiments to corroborate that the computer simulations are done in a proper way, okay? So, and in this particular case, what we observe it is that when out of the multi-scale computer simulations, starting from DFT, molecular dynamic and object kinetic Monte Carlo, then basically what we observe it is that in the nanostructure samples, we are creating a large density of vacancies where the hydrogen is accumulated, okay? And well, this was another thing, okay, and this is an example of a study of the permeation and corrosion barriers to be located in the breather blanket, as David told yesterday, but I'm running out of time, so I'm going to skip this one here. And then, well, let me straight this point, which is also very important, okay, and it is the importance of carrying out as much as possible in situ characterization, okay? Well, here, this is a schematic view of what we have to do when we carry out ex situ characterization of the materials, okay? So basically, we go to the characterization facility, whatever it is, okay? We take the sample, we characterize the sample, we take the sample, we go to the irradiation facility, we irradiate the sample, we are lucky if the sample is not activated, and then we take the sample again and go to the characterization facility and characterize the sample again, okay? Whereas if we carry out in situ characterization, that means that we are characterizing the sample during irradiation, okay, when being irradiated. And this was a setup, okay, what I saw here, which was developed by Ovidio Peña, which belongs to our research group. And well, basically, this is to measure the optical properties of the sample when being irradiated with ions, okay? So, well, in this particular case, this is the one experiment, which is in situ characterization. Basically, the objective was to study the performance of silica under Swift heavy ion irradiation, okay? And, well, they were irradiating silica with fluor at 5 MeV with high energy. And then, okay, they were carrying out in situ experiments, and this is the video you may see here. Okay, so you see, this is the reflectance of the sample, and this is the wavelength, and you may see here the chains, and when increasing, you may see here the chains, okay, in between the red and the blue curve, when increasing the radiation fluence, okay? So basically, this is what you are going to see in the video. And, well, you may see this is for every particular fluence, okay? So it is not that we measure the sample, we take it and we measure again and so on, okay? It is that we can characterize the optical response in situ, and out of this data, well, by using models, you can characterize, for example, the ion track radius and so on. So you can really obtain very valuable information, okay? So, well, this is very, very brief summary, but I hope I let you know about the importance of developing materials for fusion, okay, and about the importance to choose the proper characterization techniques. So thank you for your attention.
Thank you very much, Raquel. Really great talk. You introduced the principle, and you took the samples. You show so many techniques and how careful you need to take. You know? The experiment seems that many times the experimentalist said, well, I make the experiment, so this is the final answer. No, no. How many experiments we saw in our lives and said, this is the experiment, this is the answer. No. You use a completely wrong techniques. And there are many, many examples in science where the experiments are not really proportional to the answer that you ask. So this is one of the messages, so many techniques, and how to use that. But I have one question, and I want to take this opportunity, Raquel, to talk about your lab, our lab.
Okay, so, well, we have a very small, okay, lab, but a fruitful lab, okay, which we don't need very large facilities, and it's basically devoted both, okay, whether to produce to fabricate this kind of nanostructure materials, but not only, okay, we are also devoted to fabricate the coatings which has as multifunctional barriers, okay, so corrosion protection and anti-permeation barriers to be used in the breather blanket. And by spattering, basically, we have different spattering setups, okay, which are even able to cover the inner size of pipes, okay, not only planar sputtering, but also coaxial sputtering. And then we have two facilities, which Antonio is on charge of those facilities, which is they are basically devoted to permeation experiments, okay, so to see how the gases permeate through the coatings we are depositing, okay, and the other one, it is the thermal desorption spectroscopy, okay, up to very large temperature, which basically allow us to obtain information about how, for example, the gases are located within the vacancies or within the defects we have into the material, okay? So what we do basically it is we measure the activation energy for that to happen, and out of that we can estimate about the kind of defects we have and the stability of the defects and so on. And well, this is a very important part of the lab, but this is very much complementary with the computer facilities we have, okay? So we are a group which basically try to go simultaneously for experiments and multi-scale simulations, okay? And this is very much beneficial because as I was telling you, on one hand, they allow us to interpret sometimes the experimental results, okay, which has not only one possible interpretation, but more than one, okay? So they shed some light into the interpretation of the results. And on the other hand, this is also very important to be mentioned, and it has not been mentioned before, okay? When we are talking about those reactors, the reality in the particular case of inertial fusion, it is that we have no facility to test materials, okay? There is no known facility able to reproduce the radiation conditions taking place in those reactors. So for us, it is really very difficult to test the material under the real operation conditions, okay? And it cannot be extrapolated because, as you have seen, the damage depends on energy and it depends on temperature and so on. So it is quite difficult to extrapolate from one irradiation conditions to the other. So all what we do with the computer simulations, it is also, we try to verify that codes are working properly at the conditions we can afford, okay? And then to have a certain reliability in the codes to go to conditions that we can simply not achieve in our lab. So that's also a very important thing to be considered, I would say.
Thank you. Any question you have? Well, if not, I make another one, okay? Just a question, comment from here. Is a question that you made, certainly, in 1 year. Raquel, that's not completely true, in the sense that you need to talk about how you use a small installation, small facilities, such as plasma focus, to make experiments, real experiments, for condition of pulses in inertial fusion, and also condition getting mechanical numbers such as those of a divertor.
Yeah, well, indeed, this is also one part of the research line, which was mainly related to the thesis of one of my PhD students, okay? And it is, we are very much interested in the pulse irradiation effects, okay? Because they affect completely the materials, the fact that the irradiation is pulsed. So while we were trying to look for different facilities, and you may have read in the past in the States, but it has been unfortunately dismantled, and we initiated collaboration with the people from the Comisión Chilena de Energía Nuclear in Chile to study, to test the capabilities of plasma focus to study materials under irradiation, okay? This could give us an answer what is going to be the effect of pulsing the material, of pulsing the irradiation. We have studied that, and the first thing, we have to determine the thermomechanical effects, okay? Because sometimes the material is not destroyed just because of the defects I showed you, okay? Only temperature enhancement play a role. And then when you have very large thermal loads, just because of compression, expansion, and fatigue, the material is completely destroyed, nothing more than that, okay? Without considering the radiation effects. And then we were doing a very careful work in trying to determine the relation between the characteristic characteristic of the plasma-focused and with the radiation environment we may achieve by using these facilities. Okay, so this was the start point, and well, we plan different experimental campaigns and so on in order to give an answer to that question. So we are in contact with different, we are a small lab, but we are in contact with different collaborations, so also with the people from the accelerators, EMAN, and so on. So we keep on moving.
This is another lesson that we get. And the lesson is that small facilities, many of them completely forbidden, or considered, well, that's something that nobody believes, started in the 80s. Well, they are very useful, still very useful, if you really know how to use that. Plasma focus is, just to say in a simpler way, an anode and a cathode. You know, an anode and a cathode. But with an anode and a cathode, you can really accelerate the ions to the energies that we need in a pulsed way. Why not? And the numbers, as Raquel mentioned, the mechanical numbers in a divertor, mechanically talking, are the same that you can obtain in a plasma focus. Well, why not to make experiments? That's another lesson. And I have another final question for you, Raquel. I think it would be nice if you explain which is the correlation in between the microscopic aspect and something that people here in engineering companies talk about macroscopic aspect. Not only from the point of view of structural, because we always, in general, in nuclear, when we talk in general, we talk about changing our properties, we immediately think in the stress, strain, hardening, and there are components like the electric materials, optics, with a completely different physics, that needs a completely different doses to be damaged that we don't consider. And the properties that we need for them, to study for them, they are completely different than what we think in structural materials. So my comment is, please, make a correlation in between microscopic and macroscopic. You characterize microscopic, but I now want to go to hardening.
Yeah, well, this is very difficult. This is a very difficult question.
But you know, it's very difficult, but you know.
Because it really depends on the property you want to analyze. Okay, so for example, this is a defect. Okay, this is a coating in which basically this was supposed to be used as a multifunctional barrier. Okay, so corrosion protection and tritium anti-permeation and tritium permeation barrier. Okay, and in this particular case here, we need to study if the coating degrades. Okay, we are not very much concerned about the mechanical properties, properly said, okay, but we are concerned about if we are created, for example, bubbles or voids, or if the material reacts with hydrogen when we irradiate the material, and so on. And we test the material trying to mimic, this was done in collaboration with the people from the CMAT, okay, so we test the material trying to mimic the conditions which take place in those kind of reactor, in the breather blanket. So we test as the positive coatings, we test the thermally cycled and the thermally cycled in the presence of electron irradiation, and then we also expose the sample to oxygen, for example, in order to foresee what will happen if we have an accident with oxygen penetrating to the chamber. Okay, and basically here there were different things to be seen. Okay, we formed secondary phases. Okay, because if you form secondary phases, it will mean that the material, it is not a real barrier to lithium, okay? You know, lithium is a very small ion which can diffuse into the material, as happened with the standard use aluminum oxide, okay? And this can be, so to say, well, not useless, okay, but if you have lithium penetrating through the barrier, then you may be in troubles, okay, because all what you are going to have, it is here, you may see the interface, this is the coating, this is the substrate, so you have here the interface, so if the lithium penetrates here, means that you are going to have an interface, or even the lithium penetrates into the uroferrosteel, okay, which is very bad news, okay, because of corrosion. And in this particular case, well, we try to correlate how are the modifications, nothing to do with mechanical properties, okay, but with the elemental composition of the film in the corrosion behavior, for example. And then this was also another thing, which was the very, how to skip this? No idea. And, well, there is also another very important thing which needs to be considered, okay? So basically here we were measuring the permeation reduction factor. So we were measuring the, if tritium, okay, in this particular case we were using hydrogen, okay, to see if the hydrogen can penetrate through the barrier, if we have created some defects into the barrier. And what we did, it was we measured the permeation before and after the irradiation, and we observed that there is no change. And there is also another very important thing to be considered, for example, when dealing with this kind of coatings or with this kind of coatings deposited on the urofer, and it is the adhesion of the coatings to the surface, okay? So we are depositing one material on the other. We are creating defects can create stress into the material, and then the material can delaminate just because of that stress. So here we have shown the adhesion of the coating to the substrate, and then we see that basically there is no delamination. So this was measured by nanoscratch technique, okay, which, well, I'm not going to explain the nanoscratch, but basically we observed that the adhesion, it is the same before to the irradiation than after irradiation. So there are a lot of properties which are not directly related with mechanical properties which need to be, which are going to give us an answer about the radiation behavior of the material.
We have a question here.
I wonder if I could ask one question. This question about what does a first wall do with pulsed and continuous irradiation, say for the same number of neutrons? And I'm sitting here thinking through your presentation, there is a pulsed fission reactor that can give pulses down to about a microsecond, fairly intense. And I'm wondering if you had like 10 pulses in a day, and you had a sample that was not irradiated and a sample that was continuously irradiated, could you study those after the fact and learn something about displacement?
Well, the point it is that when dealing with the first wall, we are very much concerned about ions, not neutrons, but ions, because the neutrons have a very long penetration rate. So the first wall is going to be almost transparent for neutrons, okay? They go up to the structural material.
You have this thinking of a thick wall blanket.
Yeah.
So it's the neutrons arriving that we have some concern about in our case, the one we're thinking about. So but I'm just thinking, anyway, maybe we can talk later.
Okay, okay.
And then molecular dynamics, are you still doing that? Molecular dynamics simulation?
Yes.
Yeah,
Yes.
we perform molecular dynamic simulation in collaboration with Eduardo Bringa from La Universidad de Cuyo.
Yeah, DFT plus molecular dynamics plus kinetic Monte Carlo. So the three different levels we touch. Maybe Antonio will talk after. So we say thank you very much, Raquel.